Hi, I'm Zack, a PhD student at the University of Massachusetts Amherst. I'll be presenting the work of myself and my collaborators on glanceable data visualizations for older adults, establishing thresholds and examining disparities between age groups. For context, glanceable visualizations aim to depict information as efficiently as possible so that it can be viewed quickly at a glance. This is often the case for visualizations on smartwatches, which depict information about health and exercise data. So why older adults? Well, recent work has shed light on the importance of exploring the intersection of data visualization and aging, but there's a lack of empirical work. Also, the older adult population is one of the fastest growing groups globally, predicted to outnumber children by 2060. These folks are increasingly using wearable devices for data-driven self-care and decision-making. However, it's been shown that poor design and usability of such devices can reduce their adoption rate. Overall, this work coincides with recent calls by visualization researchers to work toward expanding the use and usability of visualizations for broader audiences. We devised our study with a few goals in mind. First, we wanted to benchmark the time needed for older adults to visually process glanceable visualizations. We then wanted to compare their times to those of younger adults, but we also wanted to see if any differences occur within the older adults age group. Once we had those observations, we wanted to use them to draw conclusions about how aging can affect our graphical perception of glanceable visualizations. Importantly, this is a conceptual replication of work by Blascheck et al. In 2018, since we made controlled changes to some aspects of the study design. The table below shows that we mostly use the same equipment, however the ages of participants as well as the study location were notably different. Otherwise, we did our best to replicate the study design and execution according to the original paper. So, how did we accomplish this? The study was done in person, so we had folks come in and sit down at a table with the watch set up, and from their perspective it looked something like this. The study centered on a single comparison task, where participants had to select which of two marked chart elements, left or right, represented a larger value. At first, we provided a standard keyboard for user input as per the original study. However, after some participants mentioned discomfort, we swapped to two separate keys, which were more ergonomic and comfortable to use. Participants were shown three possible visualizations, bar, donut, and radial, for three different amounts of data, 7, 14, and 21, resulting in 9 total possible conditions. Each trial would consist of the same set of steps repeated for various conditions. First, participants would be shown a stimulus for a predetermined amount of time, and we'll talk a bit more about that later. Then, a set of intervening images would be shown to prevent after images. The watch would then prompt the user for the answer, and they had to click left or right, and then it would tell them whether they were correct or incorrect. So, how do we decide the amount of exposure time? We use an approach called the staircase method, which adjusts the exposure time after each trial in order to estimate the participant's true minimum. We start with a large exposure time for the first trial, and each correct answer after that leads to a decrease in exposure time until they get their first incorrect answer. When that happens, it will increase their exposure time, and when the direction of adjustments changes, either from increasing to decreasing or vice versa, we call that a reversal. After that first incorrect answer, it takes 3 consecutive correct answers to decrease the exposure time, while only 1 incorrect answer is needed to increase the time. This continues until the participant finishes their 15th reversal, at which time we calculate their threshold as the average exposure time from the 3rd reversal to the end. This process comprises one staircase, which would generate one threshold value for one condition, for example, bar with 7 data points, for one participant. Thus, each participant had 9 total data points. It is important to note that due to the nature of this process, the total number of trials in a staircase can vary for each condition. However, all participants completed 15 reversals for each staircase. With that in mind, we can talk about the overall study structure. It started with a pre-study questionnaire, followed by their first set of trials for one visualization in each of the 3 data sizes. Each set starts with 10 practice trials, after which we begin a staircase. After completing all 3 staircases for the first data type, we would ask participants what strategies they used, if any, for that set. We would then repeat this process for the remaining 2 visualizations, concluding with a post-study questionnaire. It's important to note that the order of visualizations and data sizes varied for each participant based on a Latin square design from the previous study. We used online and print advertisements to recruit for the study, getting 4 participants for the pilot and 24 for the main study. Of those people, 12 were in the young old age range, 65 to 74, and 12 were in the old age range, 75 or older. Over the course of running the study, we had a few noteworthy inflection points. First, we began allowing participants to skip the radial condition for 24 data points, as some mentioned discomfort and inability to distinguish the arcs. A bit later, we replaced the keyboard with 2 separate keys, as mentioned before. Overall, we had 7 participants choose to skip the radial 24 condition. Let's see what happened. We started the data analysis by creating bootstrapped 95% confidence intervals of threshold times for each condition and age group. To compare 2 confidence intervals, we calculated a metric used in interval analysis that we referred to as interval overlap percentage, or IOP. This quantifies how much, if at all, 2 intervals overlap. If that number was less than 0, there was no overlap, indicating strong evidence of a difference. If the value was between 0 and 0.5, we would classify that as weak evidence. If it was greater than or equal to 0.5, there is insufficient evidence of a difference. For just older adults, we noticed a strong tendency of radial charts to require much more exposure time across all data sizes. We generally found that bar and donut were similar, however, as the data size increased, the gap between them increased. Comparing older and younger adults, there were 5 conditions for which we observed strong evidence of differences, including all bar charts, 2 conditions with weak evidence, and 2 with insufficient evidence, both from donut. Within the older adults group, we also observed strong evidence of differences for 5 conditions, including all of bar, weak evidence of differences for 2 donut conditions, and insufficient evidence for 2 radial conditions. Comparing younger adults to each of the older adult subgroups, we found something especially interesting. Between younger and old adults, 2/3 of conditions had strong evidence of differences. 2 had weak evidence, and 1 had insufficient evidence. Meanwhile, only 1 condition had weak evidence between younger and old adults, and the rest had insufficient evidence. Strategies for completing tasks included making a judgment with only 1 element, using more general shapes/patterns to estimate, and attempting to quickly evaluate both elements and compare. During the post-study questionnaire, we asked participants about their preferences for each chart, as well as the confidence in answering for each chart for each data size. Older adults generally showed a preference for donut greater than bar greater than radial for both preference and confidence. Younger adults were similar, however they had bar greater than donut for preference with 7 data points. Old and old adults shared the donut greater than bar greater than radial preference and confidence for all data sizes. We also asked participants if they owned a smartwatch. 6 of them did, and they said that they used it for things like tracking their health, activity, the weather, and making voice memos. We also asked those 6 participants if they preferred viewing data as a visualization or as numbers. 1 of them said that they preferred visualizations, and the other 5 preferred viewing numbers. For the 18 who did not own a smartwatch, the main reasons were due to lack of need, a lack of interest, and high costs. We also asked participants what types of data they would want to track on a smartwatch. Compared to younger adults in previous work, older adults showed noticeably more interest in tracking blood pressure, distance traveled, and phone battery. So, what does all of this tell us? We first note that older adults often require longer exposure times to complete the tasks accurately. However, between the 2 age groups, participants' relative performance for different visualizations and data sizes followed a very similar pattern. This suggests that changes with aging may negatively impact speed, however other aspects such as preferences may not change with age. These differences in time might be important in scenarios where looking at a watch for too long can be dangerous, such as exercising. However, further work is needed to understand how this would manifest in real-world scenarios. The difference in our results for old and old participants illustrates the importance of recruiting a diverse set of ages, even within a specialized age range. If we had recruited primarily 65 to 74-year-olds, we may have erroneously concluded minimal differences between the 2 age groups. Future work in this area must make sure to capture a wide variety of ages to properly sample as heterogeneous of a population as older adults. After working with this vulnerable population, we observed a possible tension between properly providing for participants and executing a scientifically rigorous study. We made small changes in our procedure to relieve our participants with discomforts brought on by the study design, and we encourage other researchers in this area to keep a sense of flexibility and compassion in mind when working with these populations. We concur with the results of Blascheck et al. That donut and bar are best suited for quickly comparing data values. However, while older adults performed well with both, the difference between them was twice that of younger adults, with older adults performing better with donut charts. We agree with recent work in this area that suggests using radial for tracking task progress for a single variable and avoiding its use for quick comparisons. We conclude with a discussion of the limitations and future work. We first acknowledge the limitations inherited from the original study. This includes the simplicity of the user task, possible impacts from the stimuli color and dot placement, and possible differences from using a watch stand versus having participants wear the watch. Additionally, over 90% of our participants had a higher education degree, though we found that education level had no noticeable impact on participant performance. Lastly, there are inherent challenges to accurately performing a replication study, especially in a different country and with a different population. We also mentioned a few areas for future work with older adults to expand on, including similar studies but with more complex visualizations and challenging user tasks, smartwatches with multiple visualizations and other information being shown on them, and, based on comments from our participants, investigating the utility of showing glanceable data graphically versus numerically. Thank you so much for watching. Please read our paper for more in-depth results, analysis, and discussion.